The first dedicated gaming GPU, the 3DFX Voodoo, launched in 1996 with 4 megabytes of memory and a processor running at 50 megahertz. That's less power than what your smart doorbell uses today. But it changed everything, because it proved that offloading graphics from the CPU to a separate chip could transform gaming from ugly flat shapes into actual three-dimensional worlds. So let's break down every major GPU feature and explain what each one does. VRAM, Video RAM. This is the GPU's own dedicated memory, separate from your system RAM. Every texture, model, shadow map, and frame buffer has to fit into VRAM, and if it doesn't, the GPU has to swap data back and forth with your system memory, which is dramatically slower. In 2026, 8 gigabytes of VRAM is the absolute minimum for modern gaming. Games like Hogwarts Legacy and Starfield can eat through 8 gigs without even trying. 12 gigabytes is where things get comfortable. 16 gigabytes is the sweet spot for gaming at 4K. And 24 gigabytes is what you need for AI workloads and professional rendering. If you're looking at a GPU with less than 8 gigabytes in 2026, you're essentially looking at electronic waste. Shader cores. These are the tiny processors inside the GPU that do the actual work of rendering images. NVIDIA calls them CUDA cores. AMD calls them stream processors. They're functionally the same thing. Thousands of small parallel processing units that each handle one piece of the rendering puzzle simultaneously. The RTX 4090 has 16,384 CUDA cores. That's 16,000 processors working in parallel. The sheer number of shader cores is what makes GPUs so much faster than CPUs at parallel tasks. A CPU has 8 to 24 cores that are individually powerful. A GPU has thousands of cores that are individually weak but devastatingly effective when working together. This is also exactly why GPUs became the backbone of AI training. Neural networks are massively parallel workloads. Ray tracing. Before ray tracing, games faked lighting. They'd bake shadows into textures, use screen space reflections that only showed what was already on screen, and approximate ambient occlusion with post-processing effects. It looked decent from a distance, but fell apart under scrutiny. Ray tracing simulates the actual physics of light, tracing individual rays as they bounce off surfaces, pass through glass, and scatter in a room. The result is photorealistic reflections, shadows, and global illumination. NVIDIA introduced dedicated RT cores with the RTX 2000 series in 2018. Without those hardware accelerators, ray tracing destroys your frame rate. With them, you can run it at playable speeds. AMD added ray tracing support with RDNA 2, but NVIDIA's implementation is still noticeably faster. Most people, including myself, prefer running games at high settings without ray tracing rather than ultra settings with ray tracing, because the frame rate hit just isn't worth it for most titles. DLSS and FSR. Deep Learning Super Sampling from NVIDIA and Fidelity FX Super Resolution from AMD. Both solve the same problem, rendering games at a lower resolution and then using AI upscaling to make it look like native high resolution. DLSS uses dedicated tensor cores on NVIDIA cards to run an AI model that reconstructs detail. FSR uses a spatial algorithm that runs on any GPU. The difference in quality used to be massive, with DLSS looking significantly sharper. In 2026, FSR has closed the gap considerably, and the latest versions of both technologies are borderline magic. DLSS can take a 1080p render and upscale it to look nearly indistinguishable from native 4K while doubling your frame rate. If you're gaming without upscaling enabled, you're leaving free performance on the table. Tensor cores. These are NVIDIA-exclusive processing units designed specifically for AI and machine learning operations. They perform matrix multiplication at enormous speed, which is the fundamental math behind neural networks. Tensor cores power DLSS, AI denoising, and the entire AI training ecosystem. When someone says NVIDIA has a monopoly on AI hardware, they're really saying that tensor cores are so far ahead of the competition that there's no practical alternative for serious AI workloads. Quick question. Do you use DLSS or FSR? Drop which one in the comments. Rasterization. This is the traditional rendering method that's been used since the beginning of 3D graphics. Rasterization converts 3D geometry into 2D pixels on your screen by projecting triangles and filling them in with color and texture data. It's incredibly fast because GPUs were specifically designed around rasterization for decades. Every game that doesn't use ray tracing uses rasterization. Even games with ray tracing use rasterization for most of the scene and only apply ray tracing selectively. Pure rasterization at 4K on a modern GPU can push well over 120 frames per second in most titles. It's not as physically accurate as ray tracing, but it's orders of magnitude faster. Clock speed. Measured in megahertz or gigahertz, this is how fast the GPU's processor cycles. A higher clock speed means more operations per second. The RTX 4090 boosts up to 2,520 megahertz. But clock speed alone doesn't tell you much about real-world performance because architecture matters more. An NVIDIA card at 2 GHz might outperform an AMD card at 2.5 GHz because of differences in how efficiently each architecture processes instructions. It's like comparing two cars by RPM. One engine might produce more power at lower RPMs because of better engineering. Memory bandwidth. This measures how fast data can move between the VRAM and the GPU's processing cores, measured in gigabytes per second. The RTX 4090 has 1,008 gigabytes per second of bandwidth. That sounds like a lot, because it is. High bandwidth means textures, frame buffers, and compute data can flow to the shader cores without bottlenecking. Low bandwidth means the GPU spends time waiting for data instead of processing it. It's the difference between a 4-lane highway and a 1-lane country road during rush hour. TDP. Thermal design power. This is the maximum amount of heat the GPU is designed to generate under load, measured in watts. The RTX 4090 has a TDP of 450 watts. That's nearly half a kilowatt just from one component. You need a beefy power supply, proper cooling, and adequate airflow. A GPU running at 450 watts in a poorly ventilated case will thermal throttle, meaning it automatically slows itself down to avoid melting. Your GPU is only as powerful as your case's ability to keep it cool. So the GPU landscape in 2026 comes down to this. VRAM determines what you can run, shader cores determine how fast, ray tracing makes it pretty, DLSS and FSR make it affordable, and TDP determines how much your electricity bill goes up. Every Linux command explained is on the screen. Go watch it next.